Are people nearly finished? I have a couple head nods. Okay. So let's talk about this. And I've rewritten, I think, enough of the detail. I jumped a few things for you. So first of all, when it's asking what is the internal energy in kilojoules, it's asking you for U. Okay? So that's always figure out what variable it's asking you for. And then it had said if at constant volume, how much energy do I need? So delta V is equal to 0. When it's asking how much energy do I need, what term is it asking for here? Just guess. CV is heat capacity. So that the units there are not just energy units. It wants how much energy. So Q, how do we know it's Q? Delta V is equal to 0, so we know that work is actually going to be equal to 0. So it's asking for a change in energy or how much energy, but all that energy is heat, okay? So for the first one, what is a relationship that we know of, internal energy of an ideal gas? Internal energy is kinetic energy plus potential energy. For an ideal gas, this is 0. 3/2 nRT. Okay? This internal energy is dependent only on what temperature this ideal gas is at. Okay? So we have 3 moles. 3/2 times 3 moles. Always keep track of your units. That'll help you know you're doing it right. Do we actually need this volume at any point in time? No. Okay? So be careful of numbers given to you that you don't actually need. Okay? And that means we don't actually need this version of gas constant either. This is meaningless to us. You'll always have them both, but 8.314 joules per mole Kelvin, and we're at 300 Kelvin. Okay? Kelvin drops out, moles drop out. What did you guys get for this one? 11.2 kilojoules. Okay. This is an example of, for an online exam, I'll tell you I want kilojoules, and so if you write it out in joules and you write 11,000 or whatever it is, Canvas will score it wrong, and then when I go in, I'll give you all but 1 point back or something for not giving me the units I wanted, something like that. Okay? And this will just be because at some point we're going to reach where we're only talking about nanomolar concentrations of stuff, and typing scientific notation into Canvas is too difficult, so I will just ask for it in nanomolar, and if you feel like you're about to write times 10 to the negative something, maybe rethink that, because I'm almost never going to ask in Canvas for you to need to use that. So that should be a nice clue. Okay? So for this part, delta U is equal to heat plus work, but work is 0. So again, we said we know that the change in energy is coming exclusively from heat flow. It's providing all of that energy. Constant volume heat capacity is dq dt. So we have a change in temperature. Delta T is equal to 15 degrees. Like I said, the size of the space between the centigrade scale and the Kelvin scale is the same. Okay. So we can rewrite this. We can plug this in as du dt. We can rearrange this as cv dt. We can integrate, so we're going to have delta u is equal to the integral of cv dt from t1 to t2. This is the actual part we want. This is what it's asking for. So this is equal to cv times t2 minus t1. This is a constant. It's 3/2 nr for an ideal gas. Okay? cv is just equal to 3/2 nr. I can plug it in, and my change in temperature is I can either write that I raised the temp by 15, so I can either write 315 minus 300 if you want to. Okay? Or you can just write that this is 15 Kelvin. 3/2 times 3 moles. What is the answer that people got for this one? 61? 561 joules? Or 0.56 kilojoules. Great. you can now definitively do some of the problems on the homework. So here are those answers. I apologize that they're blurry and difficult to see. 11.2 kilojoules. This should be 0.56 kilojoules. If instead I held the pressure constant, would it take more, less, or the same amount of energy to raise the temperature by the same 15 degrees? Beautiful, more, okay?